All right, class. Welcome to the lecture on electricity and electrical construction, um, technology, and management. Today we're going to go obviously into a little bit of the history on electricity, um, how it's associated to building construction and today's trades, and then go from the history into figuring out the loads that are required for power requirements for your buildings, how power is generated, what are the different forms of power generation that we use in this country, and then take you through a little bit of details of electricity as it's on through into your building, from power plant to individual light bulbs and outlets in your facility. So take you through those steps. Obviously, we're not expecting anyone to become a electrical engineer based on this class, but what we will be doing is going through terminology and terms and some very basic simple calculations in regards to loads in the building and things like that that you should be familiar with if you're doing construction or thinking about financing a facility and understanding how this all works. So it's a nice introduction to the total concept of electricity and how we get that to the buildings. So obviously we all know Thomas Edison. It's a great inventor of his time. Came up with the idea of electricity, and we think back to Ben Franklin and the key at the end of the kite, knowing that there's electricity that was out there in nature, and that was in the 1700s sometime. And it wasn't until the 1800s that we developed the light bulb. We relied on lanterns and oil wicks and stuff like that to use as lighting. Electricity became the immediate replacement for those things, to use that for lighting, and then obviously for other forms of use like power and things like that. So that took 100 years to get from that discovery of electricity all the way through the light bulb, and then only 140 years later, here we are, and we're into the age of wireless technology and needing power for just about everything that we do on a daily basis. All right, so 1891 was basically the time where that started to transform what we did, where we weren't relegated to doing things only by daylight, and we could go into buildings and utilize the interior of buildings until later hours in the day, to speed up production, to build more things, and it was almost like an industrial revolution here in the U.S. as well. So the bulb is a simple concept. Electricity flows into it. There's a switch somewhere before the bulb. Once the switch is flipped, electricity continues to flow through the wirement, heats up the filament inside the light bulb and the gases within it, and creates the glow that you see in the light bulb. So once that discovery was made, we link back to our first class where we talked about how New York City was prime for building construction, in that we did have already a layout of a street grid, and that kind of facilitated itself over into the electrical world as well. So when Thomas Edison decided to do his first electrical power plant, he did it in the Lower East Side of Manhattan, where one plant could theoretically service the largest number of people it could in a small area. So what it did was, he opened up that plant on Pearl Street in Lower Manhattan, and utilized steam engines to develop the power, and we'll talk a little bit more about how that gets from some form of energy into electricity, and that it could power up to 1,400 light bulbs simultaneously. And so that was the first initial power plant here in New York City. And Edison used the theory behind electricity called DC, or direct current. Basically, there are two competing forms of electricity, DC and AC, in the way it's supplied. Direct current is a continuous type of current that's applied to whatever you're using, whereas AC is called alternating, in that it has peaks and valleys, it goes ups and downs. And really the difference is, over long periods of times and distances, DC power can get very hot, even though it's a continuous higher form of power, whereas AC power alternates, remains cooler, and can go over a longer stretch of distance. So here in the US, what do we have, or more particularly maybe even in New York City, what do we have as our sources of energy? Now the theories here are basically, they go back to basic physics in terms of what we call conservation of energy. To create electricity, it has to get that energy from some other source, and it gets converted over into electricity, obviously, except for, like electrical storms, where lightning comes down, and that already is electrical energy, but doesn't necessarily get captured and turned into electrical energy. So somehow we have to generate that. We have to generate the electricity, and that energy has to come from somewhere. So here, obviously, we have a number of ways of doing that. There are power plants where we burn coal, natural fossil fuels like coal, oil, gas, and in that heating process we develop energy, and that energy goes through a generator and turns into electrical energy that can be used to power up our electronics. Other sources of electricity include nuclear, geothermal, among others, and we're going to go into greater detail here. So take a minute, see if you can think of another couple of forms of how we get electrical energy sources here in the US, and we'll go on and go through each of them briefly. Okay, so we talked about basically burning of oil or natural gas or even coal, which you see on the far left, and then second from the right. So fossil fuel type energies that are burned where heat is created, and that heat then in turn turns turbines. Those turbines generate electricity, which are transmitted then through power lines to wherever it has to go. Same concepts through nuclear, hydraulic, and we'll look at those in a little more detail in future slides. Solar power, okay, wind power, two of the more common, well, not common, but let's say the more known but less common types of generation, and that they're still not as economically efficient as some of the other methods, such as nuclear or fossil fuels, and that more has to go into it to get the same amount of electricity at this point. However, technology is advancing to the point where that's becoming a lot. The gap is becoming narrower, and as we see now, we have total electric cars, solar powered things, and we see wind turbines popping up a lot more often than we used to, which generate electricity. And that's used to supplement the major sources and try to reduce our carbon footprint and become a little more environmentally friendly in the ways that we do create our power. All right, so the breakdown of the Con Edison fuel sources here is that per their information, they use about 24% of the power they create comes from nuclear, whereas about 62% still comes from the use of gas. All right, so we're still heavily dependent on gas. There's still, which I didn't know, there's still some reliance upon coal burning to develop power in Con Edison, which I really didn't realize. I thought we had done away with all that. And then, they are breaking into trying to increase the amount of solar and wind power, which you see is at about 5 to 6% of their total fuel sources. All right, so water generates 4% in hydro, and then biomass and other types 1% or less. All right, so as you see, Con Edison does have numerous ways of developing electrical power, again, heavily reliant on gas. But there are other ways, and it supplements, what it needs to do in gas, and each of those ways are a little bit cleaner and environmentally friendly. Now we saw biomass, and that's really developing energy from biological sources, meaning basically meaning refuse, garbage, landfills, or even growing crops that can help lessen the load on the gas and the oil and coal need. In fact, gasoline nowadays, many forms of gasoline, you'll go to the pump and you'll see if it has ethanol, and that's really a byproduct of corn that's mixed in with gasoline that has many of the same properties that keeps the gas, to the octane levels that are needed for a car, yet it reduces the amount of pure gasoline that's needed. So there's ways like that that we're trying to also, again, reduce the carbon footprint, find sources of energy that can lead to electricity or in some cases gasoline that can power our devices while being a little more friendly to the environment. So hydroelectric is probably the most common form and well-known form of electrical generation. We've all probably seen, pictures of the Hoover Dam or the Niagara Power Generating Facility over by Niagara Falls. And the theory is simple. The dam is used to build up a storage reservoir to a high level. When the flood doors or the sluice gates in the dams are opened, that water flows downhill towards a turbine. The onrush of the water has power and energy within it that turns the turbine, which in turn uses a generator to generate electricity. So you're using the water power to generate electricity, and then that electricity is then transmitted out, in multiple areas wherever it's needed. So that's the most typical. So you see this around rivers, around falls, around areas where they can build dams, and wherever there is water, there's an opportunity to have power. Or running water, I guess, there's an opportunity to have power. So this is the Niagara Falls Power Station. It's basically the same concept as the dam that you just saw. When power is needed, the gates are opened up within the upper levels of the dam. That water rushes down towards the lower. As it makes its way down towards the lower, the generators are turned through a turbine, and the electricity is generated. So where you don't have, that excess amount of water, but you do still need water for this version of generation, is coal generation. You're basically burning. The heat turns the water into steam. That water supplies steam, goes up and turns the turbine, which is connected to a generator. And as that spins, it creates the friction and the electricity needed. And the electricity then gets transmitted out to wherever it's used. And the same concept is used in terms of wind. So instead of using water or steam to try to turn the gears which are linked to the generator, you're using wind power. So you have a propeller-shaped thing that catches the wind. Every time it turns, it clicks over, the shaft turns, hits your generator, the generator generates power, and is captured in the form of electricity. So a little more complicated is the science behind solar generation, but basically it's the same concept of keeping energy or conserving energy. There's energy that's contained within the sunlight. Obviously, if you put something out into the sun, it heats up. So it has energy and is creating energy. And that energy is now, we have the ability to convert that energy that comes from sunlight into electrical energy through these solar panels. Okay, and then lastly, we kind of forget that in this country, Con Edison uses or generates 24% of its electricity from nuclear power. We tend to forget that, across the country, we still actually use nuclear power for about 20% of the generation in this country. And, that's hard to imagine, in that we haven't really built or commissioned a new nuclear power plant in probably, it's got to be at least 24 years now. I mean, in the 60s and 70s, it was a big deal. That's the way the country was headed. Nuclear power was on everybody's mind until there started to be safety concerns and accidents. And, it kind of scared away producers of energy and power from using nuclear energy. So we're at the point now where, we're still trying to get back into that role. And, a lot of modern countries around the world rely on nuclear energy for, huge percentages of their power production. If you look at countries like Japan and France, they probably produce about 80% of their power through nuclear generation. And that's good, clean, energy production that doesn't require burning fossil fuels, doesn't have the emissions that coal does. it basically, there's a nuclear reactor core, and what happens is the water, again, is used to cool that, and that water creates steam. So very similar to the theory behind, burning oil or gas to develop steam that turns the turbines that are linked to the generator. It's the same theory. I mean, the heat comes from obviously the nuclear reaction, which has a long half-life. So a nuclear reaction that's contained within these cores happens year upon year without having to replace the material. But the issue with nuclear reactors is A, safety in some people's minds, and B, how do you dispose of those nuclear materials as you need to replace them as they get old. So where to dump that, where to put it. We can't just keep filling it into a hole somewhere in Nevada and think it's not going to have any impact on the environment and stuff. So, those are the hiccups still with nuclear generation here in this country. But it is a viable, cleaner source of energy, and, one that can create a lot of energy. So again, countries like Japan and France use it almost exclusively for power. And we did see a few years ago how dangerous it can be. In extreme situations, like in Japan when a tsunami hit and devastated one of the nuclear plants, and leaked nuclear radiation out for quite a bit of time there. So again, with the ability to create this power, there have to be fail-safes and things built in so that accidents don't happen. But in this country, it has slowed our progress in terms of nuclear power. So again, tidal, as the tides go in and out. We have hydrofoil blades, which are typically, you could think of these as like propellers underwater. As the tide rushes in, that there's force and there's energy behind it, because it can practically knock you down if you're standing up when, a wave comes in. So as that wave comes in, it pushes the hydrofoil, it rotates, the shaft that it's connected to into a generator, which then again sparks up and creates electrical power. And then as that same wave comes back out, as the water pulls out, it's also spinning another set of turbines, which also turn and create power. So tidal turbines are being used now more commonly, and are starting to become a valid source of electrical power. Okay, and then again, there's the biological basis of energy, where gases and fuels developed from biological sources. As you see, there's a number of examples here, but the same thing, it's using the energy that's captured from them. Again, same concept behind fuel cells. This is a more of an innovative approach to try to get power. And basically, they're coated with special materials that react with the chemicals in the fuel that create the energy. And that energy is then captured and turned into electricity. Right? And we're always looking for ways to improve processes. There are ways now, even in the recycling process, where some of the energy developed while recycling is they tried to convert that into electrical power as well. And lastly, what has become a common use of landfills is trying to capture the methane gas that escapes from a landfill and use that gas and turn that into electrical energy. So again, underground, as deposits in a landfill start to react with each other and decompose, methane gas is created, and that gas creates force underground. And what they do is they channel a couple of pipes to where they expect this methane gas to be, and the gas escapes on up through the pipe and causes pressure. And that pressure basically gets turned into electrical energy. All right, so as you can see, there's many ways to develop and create power, and that power is conserved in some form of electricity and distributed out to where we can use it. So what we'll do is electricity has a couple of common terms, which we see here. All right, an amp kind of refers to the flow of energy. Voltage is the amount of force that energy has. Resistance is kind of like the friction or the losses Much like water flowing downhill will eventually slow down, because there's friction associated with it. It has to go around rocks, it goes into cracks and crevices, and eventually loses some of its momentum and slows down. Similar to a bus, if it's not going at like a very steep incline, eventually it's going to slow down even if it's pointed downhill. All right, so there's friction, there's other resistances that reduce the amount of power or the quality of that power as it gets to its destination. Watts are your total power. You might be familiar with that term from when you purchase your light bulbs, and you know that the higher the watt number, the brighter the bulb is. So that's the amount of power that goes into that bulb. Okay, so if it's rated for 100 watts, it can take a lot more power and it'll emit a brighter light. Okay. So here in the US, alternating current is on what we call a 60 hertz frequency. And in other countries around the world that use AC, they actually use 50 hertz. And, as we've all known, if we've traveled overseas, we have to use some kind of power converter. They have different plugs, and they actually have a different frequency in their current. So you have to accommodate that so you don't fry your device or whatever it is that you're trying to plug into their power system. The way we initiate power to our buildings is that you have to go contact the utility, and in our case it's Con Edison here in New York City, and provide them a load letter saying how much power you need to get to your building. And there's an engineering calculation that goes into that to determine how much power you need to request from Con Ed to make sure that all your systems run, all the lighting runs properly, all the outlets can receive the amount of power that it needs to, and that if everyone is plugged in somewhere, you still have enough juice in the building to keep everything running. So that's developed and submitted to Con Ed, and Con Edison is required to bring that power to you in what's called a property line box. At the property line box, you make your connections to your equipment, and from that point on, it's your responsibility to get the electricity up to wherever it's needed, whether it's an outlet, a light socket, whatever it might be. All right. So again, electrical energy, this is somewhat what the inside of a generator will look like at times. There's a shaft and a spinning wheel, frictions created, whether it's magnetic, whatever the way it is created. It then gets captured into an electrical coil, and then that energy is released out. And there's ways to control it, ways to limit it, and that's how the DC and AC power production happen. This is kind of a little bit of a diagram to show schematically how things work. All right, just like in a pipe, when you open the valve, it's like a light switch. The power then starts flowing through your conduit or through those electrical wires, the copper wires. And pressure in that pipe flow, how fast and quickly and how much energy you have in there is similar to your voltage. All right, the rate of flow is known as the current. And then friction is the amount of resistance, or resistance is the amount of friction that the electricity encounters as it tries to get to its destination. So all that is taken into account when trying to figure out electrical loads. And similarly, we haven't touched this yet for plumbing. It's very similar. You go through that same analogy with water, trying to get it up to whatever level that you need of water on the 20th floor or 30th floor. It's the same kind of thing. It's kind of like you have a valve. What's the capacity? What kind of flow do you get? What's the resistance in the pipe and gravity? And then how do you get it to where you need to get it? Right. So attached here is an example of a electrical load letter that would go to Con Ed. And it would sometimes include calculations, and sometimes it would just be a letter requesting exactly what you need. So here, as you can see, it kind of gives nice detail as to how the loads and the demands are developed. Lighting equals so-and-so, exterior lighting at the building equals so-and-so, computer power at receptacles. Now receptacles are just a fancy term for the sockets or plugs that we all know that we stick our or outlets that we stick the power end of our cables into. All right. So they have the computer power ones. They have the general purpose ones. They have motors that they're accounting for in there for air conditioning. They've got the hot water heater linked to electrical, so it's an electrical hot water heater. And they put all those demands together and they come up with the total load. And then similar to a factor of safety, when you're developing your service size, So you add a certain percentage to it. So in this case, they add a 25% factor to it, and that's the request that they made. They said, I need 112.8 kilowatts to be able to come to this building. Con Ed will take a look at that, find out where their closest source of electricity is, bring it out to the closest point of their system to your facility, and then tell you here's where you have to come. Con Ed would monitor the connection between that line box and wherever your breaker panels are, and then from that point you have to distribute it into your building. Right, so another important term in electricity is grounding. Grounding gives electricity a place to go so that it's dissipated into the earth's basically there's a ground wire or ground pole or cable that can take stray voltage and insert it down into the ground where it dissipates and it doesn't shock you. So grounding is an important concept, and basically it's used for safety. So here's an example of what a ground rod would look like. And again, to distribute electricity, copper is one of the best materials, and that's what wiring is generally made out of. So it's a good conductor of electricity. And meanwhile, most copper cable is then wrapped in some form of rubber, which is an insulator, which prevents the electricity from traveling outside of the copper cable. So when you're working with electricity, you always see folks using rubber gloves, having rubber-toed boots, rubber-soled boots around, and then depending on the levels of electricity and power that you're working with, some folks from the electricians or the railroads will actually have clothing that's electrically resistant and is rubber coated to prevent any kind of electrocution or power issues when you're working with the power. Alright, so we'll stop here. We'll call this the first part of the lecture, and we'll pick up right away in our next slides and move into building electricity. Alright, let's pick up with part 2 of the electrical lecture here. Now we've all seen this. This is a very typical outlet that we might have at home or in our offices. If your building or facility has been built in the last 15 or 20 years. Alright, prior to that, you might see just the typical two-prong outlets that don't have the ground fault current interceptor type outlet. And really all that is that it has a check there where you can shut off the circuit, reset it, and make sure that it'll pop if it gets overloaded, so that you're protected both on the system side and on whatever device is connected to the outlet. Alright. So this is what it looks like on the inside. If you take the face plate off, which is the white rectangular item that you see there that holds in the or covers the rest of the wall opening around the outlet. So this is what the outlet looks like on the inside. And basically, the mounting straps, are on the top and bottom, and that's screwed into something, probably into a small metal pan behind the outlet in the wall, so that it can be held into place. And then when you see the terminals, those are actually where the electrical wire coming in on one side and then out to continue to flow on the other side. Alright, so it comes in and it comes out, so you have to be connected on both sides to keep the flow going. And the reason that's important is because sometimes flow is in what we call series, where it's one wire that's connected to a number of these things, so it's continual and they all have to be strung together and connected, and the load is such that whatever's plugged in there can be supported by that load. Or it could be in parallel, where it terminates on the left side of this terminal, and that's the last the electricity has to travel, and there could be a number of those that then get led back into a portion I'd call downline from the receptacles here. So depending on the type of electrical system you have, both sides could be wired and could continue into another outlet down the line. So the grounding slot is the big roundish plug on the bottom, whereas you have your hot and your neutral as the two prongs that are typically on every device. So there's a number of code requirements when it comes to electricity, because obviously we have to maintain safety when it comes to electricity, as it's a very powerful thing, and it's a very deadly thing if it's not treated correctly and respected for the power that's there. So electrical code is meant to regulate what can come in and come out of the buildings and the amount of power that's needed to maintain everything that's running, the size of cables that are required for particular loads. So they're all correlated. Basically, the higher the load, the more energy that's within that cable, the bigger the copper cable must be and the insulation around it. So obviously the wiring gets thicker and thicker if it has to handle bigger and bigger load. Alright, so you would expect that most of the Con Ed cables that are around the city are these huge cables, whereas by the time you get to what's supplied into your wall socket, it's a very thin cable, and we'll go through some of the cable sizing. So typically a 12 gauge or number 12 AWG American wire gauge is the most typical size of wiring, not only in commercial applications but home building. Sometimes number 14 can be used, but typically it's number 12. Okay. So you'll have a chart. I'll show you a chart that kind of gives you an idea of what each of these numbers equals in terms of size of the wire, all right, and what their capacities are. And we've all heard of circuit breakers, all right? So in every house or every building, every apartment, there's a circuit breaker panel. And some of those used to be fuse panels where there were actual screw-in fuses. But more typically today now we have a circuit breaker panel where if there's an overload on a particular line or circuit, it trips so that the wiring and whatever appliance or device that's plugged into the wiring doesn't get damaged or trips and causes fire. So it trips it out so that at the circuit breaker, and what a circuit breaker is it breaks the flow of electricity through that line. All right, so if you've ever loaded your circuit, you know what happens. It trips, the lights go out, or whatever device you were using, the power goes out, and you have to go back to the circuit breaker and reset it so that electricity starts flowing through there again. So what that is basically the safety device, and then not just building, but every major device that runs on electricity has some form of circuit breaker to it, which monitors and regulates the amount of electricity that can go through without causing damage. And that's really required when you have electrical devices. So where you have a 15 amp circuit, you're really not supposed to load it more than 10 amps, and the code has these restrictions. If it's a 20 amp circuit, you really maximum should have only 14 operational amps on there, and then on a 30 amp circuit 24. So you're kind of playing safely here by never going up to the maximum amount that circuit can handle, because at that point you're just pushing the limits. Okay. So here is the table that basically shows you the number of wire. All right, so again, it's kind of counterintuitive in that the lower the number, the thicker or bigger this wire becomes. So it goes to the large size on this table is a 4/0 or 40000, 4 zeros. Okay, which has each wire in that cable will have 0.46 inch diameter wire. Alright, and then you go all the way down to what number 14 looks like, and it's only 0.06 inches in diameter. So that's the distance across the cable. Okay, across the face of the cable. So it goes from basically a ½ inch to what amounts to about a 1/20 of an inch, this range of wiring that you see here. So obviously the smaller the cable, the higher the resistance. Okay, because there's not as much area to carry the energy, whereas the bigger the cable, there's less resistance because it has more copper to go across. And then inversely, with the lower resistance comes the higher maximum current that you can have, and that's measured in amps. Alright, so basically, if you're using the smallest wire, you have the smallest diameter. You have high resistance in that diameter, so it limits the amount of current you can carry. All right, so with the low current comes higher frequency, and this is all based on the engineering calculations that go into electricity, where voltage is equal to the current divided by the resistance, or V equals IR. Alright, so electrical diversity is a term that's used to protect against over-designing a system, basically. Alright, so again, we talk about how engineering calculations are used to develop the load letter, and that load letter gets multiplied by a little bit, so you know how much, you get a little extra supply so that you never get undersupplied. But again, you also have to take into consideration that your building is not always going to be maxed out in terms of usage. There's if you consider a 50-story office building, it's unlikely that if you calculate out for 50 floors of continuous activity where every single outlet, power supply, and light is turned on, then you're probably over-designing your systems. There's chances are there'll be spaces that aren't used, someone's on vacation, out sick, not every computer is in use at all times. So usually a diversity factor of 0.9 is used to determine what really the peak load would be. So say in the example here in bullet number 3, 125 kilowatts would be the total load if every single thing was turned on at all times. And we can safely say that that's probably a 90% of that load is accurate as your peak load. So again, it comes down to devices can be expensive, so we don't want to always plan for the worst case scenario when we know that's not going to happen. All right, so the way you'd also protect against that is even if you have that diversity factor included, your electrical panels are designed to have or accommodate a much higher rating than just the rating of the overall panel on an individual basis. So that's how you kind of protect against that. Okay, so transmission, we've talked about generation. Okay, so we've got power coming from somewhere, and we use some way of getting power generated, and now we have to get it somewhere. All right, so the power company has to transmit this electricity long distances to get it to you from that dam or oil plant or gas plant or nuclear plant, and it basically travels along wires. And what we use to do that is what we call three-phase alternating current at this point. All right, so sorry about that. So the power gets transmitted, stepped up, so that it comes at a very high voltage across. Gets to a transformer at about 480 volts, into a distribution panel, through an electric meter. At that point, that's where it's measured, how much juice you're consuming on a basis, usually on a monthly basis. It'll measure the electrical use on a monthly basis. It'll go from that meter towards a transformer, which converts whatever electricity or whatever voltage it is coming into your building into the usable 110, 220 volts or whatever it is that your building is running off of. All right, so typical is the 110 volt. We see that on all our appliances and stuff. Okay. Now the electric bill has a number of items attached to it. They talk about the total kilowatts, which is your usage, how much electricity you actually used. There are demand charges, and there's delivery charges. Okay. So alternating current was eventually selected, and that was what we saw that Edison was a fan of direct current, and then Tesla and Westinghouse developed alternating current. And it was found that alternating current could transmit electricity at much greater distances and keep things much cooler so that it didn't overheat or it'd melt. whereas direct current can provide much more higher levels of electricity, but it has its limitations in that you can't take it too far, and the further you go, the hotter it becomes, and it has other issues at that point. Direct current is still used in a number of applications. A typical example I can give you here is on transit lines, all right, trains. Third rail power is basically DC. All right, so it's a very high form of electrical energy that's needed to run these large trains and move them. So there you can directly connect. So obviously it's a live wire. There's no insulation, so you don't have to worry about the melting or the heat buildup because it's always exposed to the air. And whenever something contacts it, you have power, and there's a steady source of power running through those rails, and that's why they are very dangerous. Never step on a track basically, or anywhere close to a track if you're not trained to work on them. So that's the theory behind direct current. There's a huge amount of voltage running through that third rail, and it's always available whenever it's directly touched or contacted. Whereas alternating current works in a number of different phases where the current comes to a high point and comes back down. Enough current to basically power the devices, but not to the point where it's overloaded and always at its peak height all throughout. All right, so that enables them to distribute this current a lot further, reduce the heats, reduce the temperatures, reduce the melting, reduce the dangers while transmitting it. So what we do as part of that alternating current is there are now ways that we use what are called transformers, which converts the power to a high voltage to send it and the transformer can step up that power to a higher voltage as it's being sent across lines, in those huge towers that we see that carry cables, those high voltage towers. And then when it comes down to the point where we need to use it at street level, it goes through another transformer that steps it down to the type of voltage that we need to use, so that there's always a higher, a high current in that wire as it's coming to us. All right, so this is typically, we've thrown the word around transformer. This is what a typical transformer will look like encased. It has a slot towards the top just to ventilate, let air go in so that heat doesn't build up within it. And what it looks like on the inside is something like this. Right, the high voltage comes in, it goes through the transformer core, it's adjusted so that the low voltage comes out. This all happens within a casement that's usually filled with oil to limit the heat. Okay, and that's what they look like in reality. So you see the big cables that come on in, and then the cables coming out, which basically transform your power to the whatever level is usable within your building, which is typically the 110 volts. Okay. So we talked about power being three-phase, and this is kind of like a strange, I guess, theory to wrap your arms around. We'll show you a diagram where you see that power is basically offset by phases. And the easiest way to describe three-phase power is that New York City DOT street lighting is run off of three-phase power. And so what happens is you have basically four cables. You have your ground and your three phases of power that are run along, the lighting that goes up, say, Broadway or 6th Avenue or 5th Avenue. And if one of those phases of power were to get cut, there's still two phases of power. All right. And what happens is the way the wiring works, the three phases are run so that every third lamp is linked to one phase. All right. So if there's an issue with one phase, what you'll see down all of 6th Avenue will be every third light that's connected to that particular phase will be dark, while the other two lights, which are connected to the other two phases, which are still up and running, will still be lit. Okay, so that's the easiest way to kind of describe three-phase power, in that there's three sources running through. There's the neutral ground that runs through all of them, and then the power is kind of split into three phases. Okay, so each phase operates at that 60 hertz. You can obtain up to 480 volts if you go phase to phase in your connection. And then the phase to neutral is 277, which is 480 volts divided by 1.73. And we'll see how that 1.73 comes up in a calculation example. Okay, so again, here's your three phases. You'll have 1, 2, 3 wires plus the neutral wire. Okay. And the way it works is that they're at their peak at different moments. Okay, so that at all times there's power running through, and you don't need to carry it at a direct high phase up at that 1.0 all the way across for every single item. All right. And so to determine how much voltage there is in a particular electrical source, there are voltmeters, and it basically measures the kind of voltage that's within them. So this is how the electrical formulas are developed. You don't have to concentrate too much on this. Just understand that there are three phases. This is what the more of the electrical drawing type things look like that show you the voltage between the phases and what your neutral looks like. Alright, so you're carrying 480 basically across all three. Each phase can get 277 volts. Just another example of how that looks like on an electrical diagram. Okay. And again, the neutral serves as that grounding. Somehow that's connected. You'll have that neutral wire running all the way through, but somewhere it's connected to probably a large copper ground pole that's situated into the ground so that any stray electricity finds its way to that, where it can be dissipated safely. Okay. So here's a type of wiring diagram that shows how each of these phases are usually connected. Okay, so you got those 4 wires running through. You got the connections to a motor. And the motor generates the electricity that goes to the light bulb and then to the outlets. Right, and each of those pieces of equipment are on a different phase of the wiring. So here is a typical power distribution plan where you see the 13,000 volts that are generated. It goes to a transformer. That transformer actually steps it up to a higher voltage, which is carried over the transmission lines, where it gets to step down to about 138,000 volts in an area substation somewhere in the city. Then it gets transformed down again as you get closer to your building. Alright, so it's stepped down to the 208, 480, or whatever it is that it needs to power your buildings. Alright, so now we're even getting even smarter on how we provide the electricity. Alright, so we went from DC that runs at this huge high voltage all the time to alternating, where you have 3 different phases that aren't always at their peak power levels. And now we have what we call smart grids, where we're taking feedback. This is almost like BIM in buildings, building information management system, but for the entire electrical network, that diverts power to where it's needed by stepping up and stepping down and changing the delivery of the electricity to where it's needed the most and reducing it to where consumption is less, so that it's not just one constant delivery of power, even if there's no need for it somewhere. Alright, and very similarly, things like solar powers solar solar panels that's used for power that basically connects into the transformers and can provide part of the power that's needed, and maybe not always all of it, but they're usually used to either store up to a battery, or they directly connect to the power supply so that it reduces the amount that needs to be generated at the front end, wherever that generation is, you know, either at the power plant or the dam. And any excess electricity can be stored so that at times of peak consumption, you have that reserve to meet whatever the demands are. All right, so Manhattan is unique, and it's very similar to just about any other municipality in that it's divided up. Okay, there's different distribution districts. All right, so Manhattan has about 23 substations, and it services all the different districts, and each district kind of has its own network of cables. So because Manhattan was phased in terms of where electricity was brought to, you know, Con Edison can actually monitor which one of these substations might be in trouble, or, you know, out of power. So they can tell if a substation is out, but a more localized repair, if it's just from the network to a building, they can't find that in a master control panel. That basically has to be called into them, say where it is, and they would send a field crew out to troubleshoot and figure out where it is. Okay. So if you pay for your electric bill, you own a home, you're in an apartment where you have to pay utilities, you know there's a number of different charges that gets lumped into this electric bill. Think about it for a couple of minutes and see if you can itemize what those items are. Okay, so here's an example of a common Con Edison bill, and you can see that there are supply charges. Okay, basically how many kilowatts you use for the month. There's, you know, just typical other charges, taxes, Con Ed fees. And then there's the supply charge. Delivery charge. All right, so not only do they charge you for what you use, they're actually charging you with how they maintain and get this, how they get the electricity to you, where the generator is. So they have to pay the generator, they have to pay for the system that links from the generator to your supply. They charge you for your use, and then there's a typical amount of taxes that go on it. Okay, so Con Ed is basically the deliverer to everywhere in New York City. But the supply can actually come from not Con Ed. They have a number of different energy suppliers that are that basically provide energy to Con Ed to distribute in their system. And if you sign up with one of them, their rates may be somewhat different, could be cheaper, could actually be more expensive than the typical Con Ed rate. So it's just, you know, market economy. You go with whoever you think is providing you the best deal. So nothing changes in terms of how it gets to your house, because Con Ed is still in charge for the delivery. They own the network that provides the electricity to you, but you could buy from the actual power that's coming to you from someone else that just gets distributed into the Con Ed system. Okay, the demand charge is based on a peak 15-minute usage in any 1 month, and it's to pay for total capacity required at the power plant. All right, and no matter what, you're still paying for it, and it's just a way of them to determine certain charges. All right. And this is basically a printout from a meter that kind of shows where that peak demand is and the intervals and timing. And when you think about things, when do we have the peak consumption of electricity? What kind of equipment puts the highest toll on the usage? Okay, whenever we typically have an electrical outage, it's in the summer, right? So air conditioning is one of the number one peak load um, culprits, let's say, right? So whenever there's heavy peak load, it's usually in the summer when it's hot, and then you have a lot of devices to take up that use that power supply, and air conditioning is the number one user, right? Especially with big buildings in the city, having to cool 100 floors within a building or 50 floors within an enclosed building where there's no airflow on a 90 or 100 degree day is no small task. It takes a lot of energy to run that equipment, and that's where we fear the blackouts and stuff like that during peak days in the summer. Right? Heating systems don't typically use as much electrical. They usually run off of oil or gas. It takes electricity to run the systems, but it's not using that to heat the building, whereas electricity is using that to run all the condensers and the equipment that creates the cool air. Okay, and load shedding within a building, if you have a smart system running your building, very similar to the smart system that might run an entire grid that knows where electricity is needed versus where it's not needed, it's the same concept within a building. All right, load shedding is that where you don't need power supply, the power supply is then reduced to that area so that you have electricity where you need it, where it's being used the most. Conference rooms that are lit, areas you have a lot of computers working on, wherever it's needed versus the couple of offices where no one's occupied for a couple of days. Those are off and there won't be power. The power supply will be limited to those offices. So there are certain tools that can be used in buildings that can monitor and distribute the load as necessary, and that's a way of trying to reduce the amount of overall current that's being used. Okay, and again, summer peak time is the when the most use is. A story I like to tell whenever I talk about peak demands and load usage is that I was once doing a project in Upper Manhattan, and it was actually a bridge project, a movable bridge. So whenever the bridge needs to open, it would swing open, and it had an electrical system connected to it that would have to move this massive, steel structure and rotate it. And just like a house or a building, we needed a Con-Ed connection that came through a property line box that hooked up to all our equipment, all the monitoring equipment and the electrical equipment that ran the motors for the bridge, just like you would have electrical service in a house. And if you operated that bridge, all right, the initial jolt of energy that it needed to free the bridge up from the standstill position to get it moving, that was basically peak demand, was the impetus to get it started, and then it would be kind of leveled off as it moved, and then you would have another spike in electrical need when you needed to apply the brakes to stop the bridge from rotating. All right, so you had these two peak periods of time where you needed some energy, where you use most of the kilowatts on the meter there. What would happen is, because that was linked to the same substation and power supply that ran these huge housing projects, you'd actually see the lights dim at night in those houses in the summer when we tried to operate the bridge, because you had tons of load, right? It's nighttime, especially if it was a hot day. It's still hot at 8 o'clock, 9 o'clock at night. It's getting dark, so all the lights come on, all the air conditioning is working in all these huge housing facilities, and then all of a sudden you have this burst of energy that's taken from the same substation down the line that's needed to run this bridge. So whenever the bridge started, you'd see like a slight dim in all the lights in that area. Then it would go back bright, and then when the bridge braked to stop moving, you would see the same dimming occur. So that's basically the idea behind peak use. There's going to be times where there's a high level, and if this was on a smart network grid, it would have pulled energy from buildings that weren't being used, or office buildings where everyone's home at night and they're not being used. That energy would be diverted to the places where it was needed, and that dimming wouldn't happen. But again, to put a network like the New York City system on that is a major undertaking, and the network is aging and needs replacement, and it might be something they're thinking about installing now, but we just don't have it in the city because it was installed so long ago. But that's just a little story to tell you, and to see how fickle electrical supply can be, and what the demands can be on it. All right, let's stop here. We'll record this as section number 2 and pick up with number 3 momentarily. Thanks. All right, let's pick up here with the third portion of the lecture on electricity. As you can see here, we have a graph that just kind of predicts what will happen in the future in terms like the forecasts of summer peak demand in New York City. As you can see, it's a gradual increase year after year as we become more dependent upon electrical energy to power our devices. Imagine the fact that there'll be more electric vehicles on the road that need charging continuously. All the devices that we're so reliant upon on a daily basis run on electricity. And then just to keep the transportation system up and running, that's also expanding, will require additional electricity. So the need for it will not go down. The same in our buildings. Generally there appears to be more and more need because of what we have within the interiors of our buildings, not only for cooling loads, but the type of lighting we use. Additional loads on it. Although we are trying to get a little better in terms of compact fluorescent lighting, things that have a demand less electricity to operate, so that can perhaps cause this line to start curving back downwards, where it's not a gradual increase, as we try to find ways to conserve electricity, particularly using smart buildings, using technology to facilitate better use of electricity. So even though this is the forecast, and chances are that is going to go up, just also because of population and the greater number of users, as technology improves, we hope that would also have an effect in terms of not having that as such a steep incline and flattening out that curve a little bit. So as you know, there are, during the summer, if you're in the city, generally larger buildings will get direction from Con Ed in terms of reducing capacity. Sometimes that includes, reducing the amount of elevators that are running in a certain bank to conserve, increasing the temperatures on the air conditioning by a couple of degrees so that there's not as heavy a load. And all this is to prevent localized blackouts on the system throughout the area, particularly if there's a heat wave, a number of hot days in a row where the system just starts getting overburdened, or the entire Northeast is in a hot streak for a long time where there's just heavy demand on all the electrical producers. So we try to do everything we can to reduce the number of incidents. All right, so there, we've talked about in general terms how everything gets to and from. We're going to go down now into a little bit more detail into the type of wiring systems that can be used to carry electricity. Typically, they're all copper-based and insulated somehow, usually with rubber or some kind of other insulator around it to prevent the electricity from leaking out of the conductor cable. And a couple of things I just want to review, again, to emphasize from the first lecture, a few terms that we need to be familiar with moving forward. Alright, so the terms, before we get further into the wiring again, a couple of things that could be on an exam, in just typical terms that we should have a good idea of a definition for, include voltage. Okay, and that's really, let's say that's similar to the pressure that pushes water forward in a pipe. It's really the push, what drives electricity through a conductor. So when you hear 110 volts versus 120 volts, 110 would typically be driving less electricity through these cables than 120, and as that voltage goes up, it just indicates that there's more push of electricity through. Amperage would kind of be like the flow rate of the electricity. It's basically like the volume of water that falls through that pipe. All right, so there's a pressure behind it, and then a volume of water that eventually makes it through that pipe, much like voltage and amperage. It's a pressure behind the electricity, and the amount of flow of electricity through that cable is amperage. When you take the voltage times the amperage, you get the watts, and that's the unit of power, and that's typically what gets measured in terms of, like when Con Ed does your bill, like we saw earlier. So you take that, the voltage or the drive times the flow, and that equals your unit of power. That's how much power you're getting out and how much power you've consumed or used. It gets measured in watts, or more specifically kilowatts, as you saw in the electric bill. So how does this all get carried? What is that pipe? All right, in terms of talking about water, we say it gets carried through a pipe. In electrical terms, that flow of water is really amperage, and it gets carried through various different elements. We can use conduit. Conduit is really just very similar to a pipe, actually. It's just a hollow pipe that does carry conducting wires. All right, so within that conduit, you need something else to carry the wire. The conduit itself is not what carries the electrical through. Conduits typically used in areas where you want protection on the cables, where you don't want your cables being cut easily. So these are basically, leading your power supply coming into your building. Might be coming through conduit from Con Ed. They could be armored cables with, thick shells, something of that nature. But conduit carries the electrical wires through. And when you need protection from potential strikes, like a shovel striking it or digging, when you have it in a shallow portion of the earth buried underground, usually use conduit so that you have that extra level of protection, so someone can't just strike it with a backhoe or a shovel and electrocute themselves. So you have conduit protecting it. All right. So within that conduit, again, you have the wiring, and it's probably the most protective thing you can have around your cables. All right, and then we use other types of protection, such as EMT, electrical metal tubing. Again, that's a protective tubing, but it's not quite as thick as general conduit. It's cheaper, but it's also flimsier. It doesn't afford you that same level of protection, but it's better than leaving it exposed. Green fields are basically flexible armored cable. And when we say armored cable, think of a water hose. Okay, so it's flexible, it's kind of rubbery, but within that rubber there's some extra reinforcement that makes it a little more resistant to being broken or cut. Then there are cable trays, and that's pretty self-explanatory. They're almost like open trays. Think of a U shape, but more or even like a rectangle without the top. The kind of open area where you can lay lay your wiring or whatever it is in there that's being carried, and that serves as the protective device, and it serves for an area to install. So you see cable trays a lot within the interior of buildings, particularly in computer rooms and things like that, in the subfloor, so that all of the wiring is kind of carried through and routed through specific areas, so that other portions of the subfloor can be used for other things, and you know exactly where all the cables are that are connecting to your boxes and stuff. So the cable tray is used to kind of not only corral all the cables, but also provide a safe haven for all of them to be put in. Now BX is another kind of, I guess, more rigid kind of wiring. We'll see a couple of examples of this to make it a little more clear. And again, it's kind of like smaller armored cable. All right, and then the bus duct is kind of like almost like the cable tray, but it allows you to carry your wiring in the vertical direction. Okay, so up from wherever you make your connection, whether it's in the basement or in the first floor. A lot of buildings have a number of different bus ducts out from those areas so that you can bring electrical services up through your building. And we'll see a picture with an example of that. All right, so other uses, there are access floors, again, like I said, much like the subfloor where you have the where you have your cable trays. You can also have a basically hollow access floor that you could run whatever you want under there if there's no other equipment or anything else that needs to be put into that floor. There's flat wiring that's very similar to the armored small armored cable and small armored wiring, and we'll take a look at some of that as well. Alright, so you can see kind of some of the armored cables to the left. Alright, you see it's kind of, it has that metallic look, it's ribbed, it has wiring running through it. BX is the one to the left, and that's one of the more typical to be run through buildings. It carries, you see your three-phase conductors plus your neutral carrying through, and it's sold as a complete set. Okay, so when you buy BX cable, it'll have the 3 phases, probably number 12 wires in there with the neutral, and you basically connect that from point to point and you're done. Greenfield is thicker, it's bigger, and that one you run your own cable through. Okay, so whenever you buy Greenfield, these are generally used for, I've seen them in a lot of temporary uses. That way you can choose and select what's running through it. Conduit, as you can see, is almost like a steel pipe. Okay, very rigid, strong, thick material. And then EMT to the right. It's tough to tell without looking at it through a cross section, but it's just a much thinner version of conduit. Okay, so generally, part of what the electrician's jobs when running they call running cable through these conduits or EMT or through the Greenfield, right? They need to get the wires through, and it's impossible to just take the thinner wires, the number 12s or 14s, and try to just shove them through dozens of feet to get to the next opening where you can pull them. So they devise a couple of tools, and really what they do is they call them, you generally either snake it or mouse it. Those terms can kind of be used interchangeably. Mousing it is by tying you get from one side with your conduit, you kind of tie a rubber bag to the wire that you're pulling through, the conductor wire that you're pulling through, say a number 12 or a number 14 type. And then on the other side of that conduit, you connect like a vacuum to it or a hose, and then you use suction on that bag to kind of pull the wire through. Once that bag that's carrying the wire gets sucked into the other side, then you've made your run, and you can tie off your conductor to wherever it needs to be. And the same can be used. They have snaking kind of coils that you see on the left, where you can shove that through the pipe from the end you're trying to get to where the cable is now, tie it to the cable, and then pull that cable back on through the conduit that you just snaked through. So there's a couple of different ways to tackle it, but basically it all requires having a tool or device to pull or push that wiring through. Alright, so here you go. This is an example of the wire fish tape coming through. He's on the pulling end. Alright, so someone else had connected to the other end, and it's coming out through there. That looks like an outlet or a receptacle over there, or even a small little junction box, depending on what you want to put in there. So you have the wiring coming through, and you're going to terminate there, and then probably shoot wire through again. Alright, so in addition to having to do all the conduit work, all of these conduits, all of these things tie into a panel board somewhere for distribution. So this is where you get your main power coming in from Con Ed, and then what happens is you distribute that power through a number of circuit breakers, and those circuit breakers feed, or the power coming through those circuit breakers feed, a number of different electrical points. whether they are lighting points, whether they are receptacles or outlets, whatever the case may be. There's a number of them connected to each of the breakers, and the breakers, as we saw, are rated for a certain amperage, and then you can only install as many outlets or receptacles or lights as those breakers can handle, or they'll continue to trip. Alright, so a couple of things to keep in mind in terms of the distribution boards. You want your panel as close as you can to your loads because there's something called voltage drop. Alright, the longer you run a voltage over a distance, you tend to have a little bit of a drop off. Okay, so almost like anything else, over distance, you tend to lose a little bit of the pressure. All right, so we talked about voltage being like the pressure behind water in a pipe. If you have a ridiculously long pipe, eventually by the time you get to the end of that pipe, you're going to lose a little bit of the pressure of the water. So the closer you are to the source, the more confident you are that you have the full supply available. All right, so we want to have these things as close as we can to where we're using them. If you have different voltage sources, you have to have different panels so they can be labeled properly, and you don't hook the wrong type of equipment to it. All right, every panel distribution board, you should probably have spares. We talk about having about 25% extra space for more circuit breakers. And the reason we do that is because you never know when you have a building that you'll need to upgrade at some point to meet the code. If code changes, if there's more access, if you expand the building, you want to make sure that each of your panels has a little bit extra in it so that you can accommodate small changes. Okay, and again, we use probably 95% of the time I see circuit breakers used, but in the old days they used to use fuses, and the problems with fuses is whenever you overloaded the circuit and the fuse would pop to protect the cabling and to protect the systems, you would have to go in, unscrew the fuse, and then replace the fuse. Whereas a circuit breaker, whenever it gets overloaded, trips, and all you have to do is reset it by flipping it back over to another side. So I'm sure many of you have done that already, in a house panel or an apartment panel. Okay. Alright, so this is basically what the entrance looks like from a main feed service. Okay, you see those heavier wires that are coming in, they go into the distribution panel. That in turn feeds a lot of smaller cabling that runs out through those circuit breakers. Alright, so each of those circuit breakers have on the other side small wiring. You see it, you don't see it there, it's hooked behind the cabinet basically, running out through the walls of the building or through the floors, and then connecting to these circuit breakers. Alright, so as you can see, these are all, well, except for one, all are on. Alright, and then one has been tripped, the 15 amp breaker, second down from the right. So that one was they're either working on, something down the line from there, and that's one of the best places to safe off if you're working on something. So you find the line that the outlet or the lighting that you're working on is connected to, and you trip it. You trip it right at the breaker, and that prevents any voltage or current from going through the wiring down the line from there. Alright, and then as soon as you're done working, you flip that back on so that you start getting the flow of current back through the wiring. And as you can see, these can get very robust. Over on the top left, you see large conduit, okay, bringing in the service feed. That goes down to the breaker panel, and then you see a lot of the other wiring that's hasn't been terminated yet. And what they do is they terminate that back later, but they run all the cable now through the conduit up top. So this is, during construction, getting close to the point where they start powering things up, but they're just running cable through. Right, and you see the color coding, the red, the black, the green, the blue, each means something for this particular setup. So the number of circuit breakers are determined by the number of elements you have. Like I said, each breaker is rated for some amperage, and every element that you have has a certain amount of amps associated to it, maybe 1.5 amp for each outlet or lighting. So you figure it's easy, as soon as you know your loads, to figure out how many breakers you need and how much service you need coming in. All right, so within the panel, like I said, we have 3 phases. So you want to make your connections so that you're not overloading one particular phased wire with more stuff than the other 2. So you try to distribute it. And the way we do that, like I said, the example was street lighting, okay, on like Madison Avenue or Fifth Avenue. If they're using 3-phase power, AC power, all the way up the avenue, and one particular phase is overloaded, and
还有，你怎么不考虑直接声波？ 如果有需要申请啥？那个是还是我也觉得自己。
And trips a breaker, what'll happen is every third light will go out and the other two will remain. So what you want to do is you balance it out so that none of them get overloaded, and you can maintain all three lights, every three lights up the entire avenue. Okay. So the panels themselves are rated for the voltage depending on what you're bringing into the system. And typically you want lighting and emergency lighting separate from the rest of your supplies because lighting is important in terms of evacuation and stuff. All right, so you could live without some other things in an emergency, but without the lighting, that's a little more difficult. So lighting generally has its own separate panel. And that's also so that if we need to work on equipment or systems, you're also not working in the dark. Okay, if a system trips, like your HVAC system or your air conditioning system, and you have to go work on it or troubleshoot it, it's impossible to do if the same circuit contains your lighting, because then you have to use temporary lighting or bring in some additional lighting, flashlights, and much harder to do. So it's always wise to keep lighting separate. All right, so this is a typical panel schedule. Alright, so basically when you open up one of those gray metal doors for these panel boxes that you just saw that have all the circuit breakers on the inside, it should list some details, including the voltage in. right? How many amps it's rated for, and then it takes each individual circuit breaker, numbers them, and then gives a brief description of where that circuit breaker leads to. Okay, and it should be enough of a description so that you can identify where it is and which portions of the electrical system in your building or floor they operate. All right, and then as you can see, even on the like the 42 circuit panel below, not every single circuit has something associated to it, so those would be your spares. And how that would be signified in a panel is that there might not be an actual circuit breaker in those locations for those numbers, like 6, 8, 10, 12. There might not be a circuit breaker, or there could be a circuit breaker already installed, but no wiring leading to them. All right. Some of them get more detailed in terms of you break out your 3 phases, so you know exactly what's connected to each phase if you get a major brownout or blackout with that service. Alright, it tells you which number circuit breaker it is, right? How many amps each of the breaker have, the wire type that connects to it, so you know if you need to replace wiring. It's a number 12 AWG. And then how many watts under each one of those. And so you see receptacle, receptacle, receptacle. Basically you have the typical, okay, all the way through all of the left side plus 2 through 12 on the right. Your microwave has a little bit higher load to it, but it still has the same size circuit breaker. The hot water heater has larger circuit breakers because, as you can see, the wattage is a little bit higher for those, 4500. Alright, so you're using a 30 amp breaker. The same for the irrigation pump, water heater. And then you break it down again. Appliances are a little more than receptacles and lighting. Circulation pump, drinking fountain, and then the computer loads are on 20 amp breakers. So when you look below, you're looking at the balance of the 3 loads, and actually, line 1 has a little bit more connected to it than line 2 and 3. It's fairly balanced, but they could, if they wanted to, could probably split it around a little bit better. Here we're actually lacking spares. We're almost tapped out here. There's only 2 spare breakers in the entire panel, number 40 and 42. Okay, we're going to take this point here to stop in the action, and then we'll pick up with the 4th portion of the lecture, and that should be the last of the lectures for electricity. Thanks. Alright, here we go in the fourth installment of the electrical lecture. It should be the last one. Let's pick up the pace a little bit and get through this, and that'll be the conclusion of electrical. Alright, so what you hear here is another way of showing basically what we saw up here in the schedule of what's inside the panel. Basically the engineering drawing version. Okay, so you see that there's a number of circuits. It's again 3-phase wiring, A, B, and C. The circuits are distributed evenly across those 3 phases. Okay, 1 and 2 on A, 3 and 4 on B, 5 and 6 on C, so on. Okay, and you go on through. It tells you there's a couple of 2-pole and 3-pole circuit breakers there. Okay, and what that actually looks like, we saw in a slide. Let me just find that. Okay, here you see a couple of 2-pole breakers, all right, which is basically 2 20 amp breakers connected there. As you see, the top left and the bottom left breaker are each actually the top left is a 2-pole, the bottom left is a 3-pole version of what we were talking about. All right, so just they're linked there. It's added amperage. They're larger items connected to those. Alright, so you need to take up 2 of the positions, alright, and 2 circuit breakers, or 3 of the positions and 3 circuit breakers to have enough capacity for those. Okay. And as we talked about with AC service, what's great about it is you can step it up to 480 to send it over long distances without getting much of a loss and not much heat. And then when you get it to the point where you have to use it, you go to a transformer and you step it back down to the 110 volts that come out of the outlets that connect to all of the typical equipment that you would connect to a traditional outlet. Alright, so that distribution panel will shoot it up at 480. You hit the transformer at the floor level. Alright, connects into your distribution panel at the 110, and then it goes out to your outlet at 110. So everything that's rated for 110 can plug safely into that outlet. So again, this is what it would look like typically. You'd have a meter up there because each floor may have a different tenant, may have different usage. So you want to be able to properly bill if you're kind of bill each of those particular users. And as a building changes, they can change where the meter is located a little bit, prior to wherever the distribution panel is for those tenants. Whether it's 3 floors, 4 floors, 1 floor, they'll be able to change the arrangement so that they can properly bill. And so again, as indicated, you come in at 480, step it down to a transformer down to 110, and 110 can safely power those appliances. And this is what a typical distribution room looks like, potentially in a basement or on the entry level. Right, all of the higher electrical equipment's in there, switch gears, transformers, etc. And then you can monitor what kind of usage is going on there. If there are any issues or major issues, there'll be panels in there which will light red or green to show you if there's a particular one that's not working. And then you see the main safety switch bars there, where if you want to work on something within it, you have to throw that switch down, which will shut the power to that particular piece of equipment. Okay, this is the riser or bus duct that we described earlier. Okay, you can see how that allows for the conduit full of the cable, bringing the 480 up the building spine or wherever it's located, up to each individual floor level. All right, as you can see, it's kind of armored and protected, so you can build in and around it as the levels go up. All right, this is a revised wiring diagram, probably for an as-built, showing exactly what was installed in a particular installation. So what happens is they give you the stamp up there on the left within the cloud that shows you how many circuits, the conduit sizes, the panel number, and the wire sizes. So this is an actual as-built, so you know what was installed in those locations. Alright, so we talked a little bit about electrical flow. Alright, the voltage is the pushing that through. Amperage is the flow rate of the electricity. Okay, and then the wattage is the unit of power. Alright, so if you have a 3 amp requirement for a 120 volt bulb, you're basically using 360 watts of electricity. Alright, this is a typical wiring diagram. It kind of shows you the 2 number 12s coming in hot. That means that's your power. You've got the ground cable and the neutral going into the other side, and that's your outlet. Alright, there'll be typical color coding throughout most installations. And you'll have a separate set, silver screws on the left, the brass screws on the right. Typically the hot wire in this case, which is black, goes into the brass screws on the left. Your ground wire goes into the green screw, and then your neutrals go to the silver screws on the left. Right, and then you would pretty much typically have that same color coding alignment through the entire building. Right, this is a typical engineering or even a field layout sketch. Alright, that just kind of gives you an idea of what's where and how it's connected. Okay. You'll see which circuit breaker everything is aligned to, and we talked about how you can have a number of different outlets or prongs or lights connected to each particular circuit breaker, as long as you're not overloading that particular circuit. Alright, so you can see that there's by the diagram here, let's say circuit breaker number 10, alright, happens to have 4 electrical outlets in the wall, and that's connected to number 10. If you go to 11, you see that it has 1, 2, 3, 4 light fixtures and 1 outlet over there. Then you get to number 9. Number 9 has a couple of electrical receptacles, 3 of them. Okay, and then number 12 also has a couple of lights, 2 light fixtures and 2 receptacles. So basically, that's how to lay out in your panel. You have four circuit breakers, and then if you needed to do work, say on an outlet in the dining room, you would trip breaker number 10 and turn that off so that you could work on them safely. So there's also a couple of what we call self-contained systems, and I'll describe what those are. All right, a generator, that's been in the news over the last couple of years, and that there's been a shortage of generators. Shortly after Superstorm Sandy, particularly in the New York area, there was a big call and need for generators. And they can basically generate electricity, and they need to use another source. So it's like having a small power plant using oil or gas or whatever the case might be. So you use that for temporary power, and then critical areas that need electricity continuously, even in emergencies, usually have these. And we're talking of emergency hospital centers, communications rooms, things that need to maintain electricity to be able to continue to function and are important. So particularly hospitals again. And there were, in the news a number of times where generators that were installed at the hospitals didn't turn on when they needed to, and you saw those stories in the news when Sandy hit. So thing is, with the generator, there's usually a startup time required for them, or even if power loss is detected and the generator is set to switch on automatically, it takes a couple of seconds for it to start up and then to be able to produce enough electricity off the bat to power up. So that's where we have what we call uninterrupted power supply systems, and you might know that term maybe from your computers or backup supplies that you have on home computers. But they have UPSs basically, or large UPSs for major pieces of electrical equipment. And what that is, it's a battery system that's constantly backed up. Maybe if you have a Verizon phone box or cable box in your house or your building, that also comes with a UPS, so that if you lose power, the UPS kicks in, and basically it's like a battery backup system that maintains power, at least for a few hours, until you can get permanent power restored. Okay, typically those are used again at cable boxes, telephone cabling, computer systems, things like that. Right, but they do have UPSs for larger things. Bridge operational systems all have UPSs, so that power goes down. The lighting doesn't immediately go down, things like that, until a generator can kick in. So sometimes UPS is used to kind of bridge that gap. And then lastly, we have what we call cogeneration facilities, which actually is used to not only provide power but also heating or cooling. All right, and basically it's a contained system. And we'll go into a slide in a little bit. That's just what a generator would look like. If you haven't seen one, that's typically a large generator that can keep a building powered up as long as you have enough fuel to keep it going. All right, so cogeneration is the combined heat and power. All right, you use some kind of fuel to create heat, and that surplus heat goes around and is used to heat water that's used in the cooling system, and again create some kind of steam, which drives an engine and then a generator, and that generator produces power. So it's kind of using every element of the system to kind of continuously feed each element of the system. And they have very, very large cogen plants being built to try to also conserve energy, basically, and keep this power going in building layouts and stuff. So we have a lot of new developments where you don't have easy access to electricity, they build their own cogen plant just to feed that facility, and that's typically used in university settings, sometimes in new development in third world countries where they don't have like a very built up or stable electrical system. If there's a new government facility being built there, it'd probably have a cogen plant. All right, so other than the typical electrical systems that we've talked about already, things that you would need within a building include a life safety system, and this is all those things that are critical for emergency services. Having pull boxes for the fire alarms, speaker systems that can direct you in an emergency, strobe lighting, and emergency lighting that shows you where the exits are for the stairs, that provides enough power for elevators to get to the lobby should there be a cut in electrical power, so everyone can get out of those elevators and escape. All right, security systems are another system that often are tied into the buildings. You know, alarm systems for doors, motion detectors, heat sensors, and security cameras, CCTV cameras. Could be part of a system. And then there's other lighting controls, visuals, and then if you have a BMS or a building management system, that would typically need electrical service and also have some kind of electrical backup to maintain the computers on the system should the electrical system go down. All right, so now we have a pretty good idea of how electricity gets to where we need it and how we use it in buildings, how it's piped in through the buildings, the kind of cabling or conduit that's used to conduct the electricity, all right, how electricity is installed. And so we take a look at the energy usage. The typical is that it's about 30% lighting, 15% of the usage on a yearly basis is cooling, 9% is heating. All right, we talked about cooling being a little more, having a little more energy consumption than the heating abilities. And of course each of those are used throughout the year, so combined really heating / cooling is like equal to the lighting, which is year round also. And then refrigerators, motors, hot water, are other big users of electricity, and office equipment, although 3%, but it's one of the major contributors as well. And then all other thing combined is another quarter of your usage, most likely in a office type environment. All right, so when we need to troubleshoot and also when we're installing to make sure that everything's the way it should be before we power up the system, there's a number of ways to test amperage, voltage, resistance, and we're going to go through what we do for that. Amperage and voltage can basically be read using a meter, so you know that your wire is hot, you got voltage coming through, you can read the voltage, and if you're anywhere close to the 110 at the end point, you know you have a proper installation, you don't have any losses or cuts in the wires or any issues along that line. Resistance is a little bit different. What we usually do is we test resistance in a cable to know that it's not cut and that it's been terminated and ground properly. So what we do is you would shoot through one end of the wire to see what the resistance is by the time you get to the other end, and depending on the reading, you would know that you have a good wire or not, and they call that Megger testing. And then lastly, obviously, electricity builds up heat, and you can use thermal imaging to know where you're hot, and that's why they call it hot, because you're going to have heat running through it if you've got a hot wire that's actually carrying electrical current. And so a voltmeter or an amp meter, basically you hook right up to right around the wire, and then you'll get a reading on it. Thermal imaging or scanning, as you can see there, you can see which wire is have some heat conducting through it, and it'll show up on the thermal imaging in a different color. Right, and then here is basically a layout diagram similar to what we saw that was a little more color-coded earlier. All right, this is the engineering version of it. It tells you which is the which circuits are which, and then you'll see the typical layout for what's a wall socket versus lighting. Okay. So here's something that could appear on an exam. A very simple calculation that kind of gives you an idea of how these circuit panel breakers and stuff are planned for in a building, knowing what your loads are. So what we have here is given in number 1 is that you have a 10,000 square foot floor. Okay, so it's a large office floor, let's say, and the average usage on that floor is 10 watts per square foot. All right, let's just say that's a standard engineering calculation for what's expected in this floor. All right, so you know you have a 110 volt three-phase system, which is the typical here in the US, right? And that you have available a couple of 42 circuit panel breaker boards that can accommodate, obviously, 42 15 amp circuit breakers. And what we want to know from this problem is how many 42 circuit panel boards do you need? Okay, so what I show you there is the formula, right, which shows you how many amps you have from this system. All right, so it's your wattage. Okay, and your wattage is solved from number 1 above. All right, 10,000 square foot times 10 watts per square foot equals 100,000 watts. All right, so that's what you fill in at watts, 100,000 watts, and you divide that by 1.73 times 110 times 0.90, which is the power factor given below. And when you do that calculation, the 1.73 is basically, we saw that earlier in probably the first part of the lecture, that shows you how three-phase wiring is calculated. All right, so that comes straight from that slide, 1.73 times the volts times the power factor. And you divide that into the 100,000 watts that you have based on the given, and that gives you the amperage of 583 amps. Okay, and now we have to take our knowledge of the circuit breakers and figure out how many circuit breakers we need. So we have 15 amp circuit breakers, and we saw earlier in the lecture that on a 15 amp circuit breaker you don't want to load per code more than 10 known amps in each of those circuit breakers, right? So if you have 583 amps altogether, you divide that by 10, that gives you 58.3, or really 59 circuit breakers that we need. Okay, and if you can accommodate 42 circuit breakers in each panel, that means you need 2 panels. Okay, so what you would do is provide 2 panels, one with 30 circuit breakers, one with 29. All right, so you have spares in each of the circuit breaker panels, and you would have 30 15 amp circuit breakers in one, and 29 15 amp circuit breakers in the other. Okay, and what I'll do is I'll put up in the resources, I'll put up a PDF of this calculation so you can refer to it and see how the problem is solved. Okay, but hopefully that description and explanation I just gave you will walk you right through it, and you won't have any issues with it. And expect to see something similar to this on the final. Alright, so that's a typical incandescent light bulb. We know we're not using those as much anymore as we used to. Okay. So lighting nowadays is more gone to fluorescent, which is the more typical in the in an office environment. And actually, what's taken the electrical world by storm is the use of the compact fluorescent CFLs. Okay, which actually use much less energy and last much longer than the typical fluorescent or incandescent bulb. The only negative part to that is that, if it breaks, it releases a lot of toxic fumes and chemicals, which is what enables you to use less electricity to keep the light going longer. But as long as you know how to properly manage that aspect, if something breaks, you really got to clear out of the room. You shouldn't vacuum it. You should just sweep it up. The less you push it around or circulate it, because it's very light materials on the inside, the better. And if you wet that area after you unplug it or take it out, to also keep the fumes and stuff from spreading, that's also a good idea too. So there's a slight negative to that, but as long as you know how to handle a situation like that, then there's really no danger in using the bulbs, and they're so much more efficient than the old-fashioned incandescent and the typical fluorescent beams too. What we're using in more heavily used areas are the light-emitting diodes, or LEDs. If you've driven down highways and seen those lights where the overhead looks like 6 or 7 mini lights, strung together that's kind of bluish, those are LED lights, and those are actually far more efficient than even the compact fluorescents. All right. And then there's a last type called metal hydride, which uses a different composition of chemicals within the bulb, but sometimes it's very difficult to get the clear white light that you need from that chemical reaction to be used, much like the other lights. All right, so just a comparison, of LEDs to compact fluorescence to incandescence, of how much power you really use for the same amount of lighting. Okay, and sorry, something I skipped on this slide. Foot candles, or flux, is how the amount of light in a given area is measured, and that can be measured using a light meter. Okay. So if you ever hear something like in a construction spec that you need during night activities a minimum of 15 foot candles over the construction area, that's how you measure it. There's meters to tell you how many foot candles, and there's calculations you can do to determine how many bulbs and how much light you need to create 15 foot candles of lighting. All right, so back over here again, incandescence, again, that's much, they're the most inefficient right now. Compact fluorescents are much better. They have a lot longer lifespan. They consume a lot less power. Okay, so your total energy usage per year is pretty good compared to the incandescent. And they're fairly cheap now. They can be mass produced, whereas LEDs, are not as cheap. They're far more expensive, and even though they give you much greater lifetime, a lot less power consumption, and a lot cheaper in terms of power, it hasn't been mass produced or developed to the point now where you can get those as cheaply as you can the compact fluorescents. So for typical home lighting and stuff like that, you'll see more of the CFLs than an LED. All right, so these are just typical, some different shapes that you can see an LED light in. And what it is, there's a light emitting diode that helps cut down on the amount of electricity needed to produce the light. All right, so again, conservation of this electricity so that we don't blow past our expected usage, and we try to, level out that line that we saw from Con Ed with that projection from 2020 on, that it continually just rises every year. The things we can do is use occupancy sensors within our buildings so that when there's no movement in an area, the lights automatically shut off so that they're not on for 12 hours until you walk back into the office the next day. Using timers to reduce the time that a light is on so that it's on only during the dark hours. Photocells are basically a device that triggers a light to turn on when it does not have sunlight hitting it. All right, so basically once things get dark, photocells go on. That's what a lot of roadway lighting uses to go on and off. All right, the use of more daylight. Okay, the way we're building our buildings, we're using a lot more windows and facades. All right, so that we can get more daylight into the building. And on top of that, not only are we using windows, but what we're doing is we're eliminating the exterior offices that used to go around the perimeter of the building and allowing more workspaces on those exteriors so people can use the daylight and reduce the amount of artificial light we need to generate using electricity to work in those areas. And that's part of the LEED requirement. Okay, what percentage of your building can be used or has what they call natural light or access to natural light. Basically, can you see out a window from where you work? All right, and then obviously improvements in technology, using those more efficient bulbs, trying to get towards LEDs or metal halides that give better light, and where we can produce those two types of bulbs more efficiently so that the cost of manufacturing them and distribute them go down so that they're affordable to everyone. So those are the ways that we're trying to reduce electrical usage. And again, we saw that 30% of electrical usage is really just lighting. All right, so if we can make a big dent in lighting, we can make a big dent in the amount of electrical consumption. Okay, so just a calculation to kind of put that in perspective. If you have old lighting that used to take up 2.5 watts per square foot, and you have new lighting, be a change of bulbs that now only require 1.5 watts per square foot. If you have a 25,000 square foot floor, okay, you can basically save $62 a day, assuming it's a 10-hour workday where the lights are on. All right, you have a 20-floor building, that's $1,240 for the entire day. 20 days per month, that's $1,240 per month, and you times that, say you have 50 stories in the building, all right, times 12 months a year, you're up to $744,000 in savings in just lighting electrical costs. All right, so that's a massive amount when you're thinking of operating a building. From his budget, you can take that 744 grand and perform upgrades, buy more efficient bulbs, do a lot of things. All right, so it can make a major impact, and that's why there's been such a rush for complex fluorescent lights and switching over to that. And if you haven't done it at home already, you should. All right, Con Ed is pushing this as well because it doesn't only although they're the provider and they make money if you don't use efficient lighting, they also have an old system, and they understand that a lot of the electrical system is nearly 100 years old. All right, the less load that's on it, the better it is. The less load that's on it, the less maintenance they have to do and continually upgrading it. They can concentrate on upgrading instead of maintaining areas that got blown out because there was too much load. So they do push this. They do want you to become greener and become more energy efficient. And there's a number of incentives, especially for large businesses, which are the primary culprit in terms of using electricity. So they have what they call the Green Team, which can come in and do a study for you. And then you can also, not only do you get the benefits of the study, but they can also give you reduced costs on the study as well. Okay. And they do that also for, like I said, residential. So if you haven't done it already, you can have the Green Team come in. They come in and they take a look at the your interiors. They take a look at your windows. They see where you're starting. If if you're actually energy inefficient because you have poor windows and stuff like that, ways to increase the daylighting, and then they'll take a look around to see what kind of bulbs you're using, if there's certain things that could use timers, and if you can use thermostats that are actually based on timers as well, so that you're not always keeping the heat on at a certain level, and you can turn it off and on when you need it. They also provide free thermostats that actually have Wi-Fi connections, so that you can actually turn on and off the heat, from your cell phone and things like that, so that when you're on your way home, you can turn it on 5 minutes before you get there and have a warm house, and not have to have the heat running the whole day, so that you can walk into a warm house. So there's a number of positives, and Con Ed sends that service out for free, basically, to look at it, and then if there's any kind of any real action that they need to take. For homeowners, like I said, many of those things are free. For larger corporations, it costs them money, so they can actually do the study at a certain cost. All right, so here's the electrical homework. Right, very similar to what we did in the example, which again I will post within the next day or two, just the write-up of the example and how that's calculated. All right, so if you could hand this in 1 week, okay, before the next class. As you know, every homework has to be, hopefully email is best. Email it to me before the next class start time. All right, that's it for electrical. Hope you enjoyed, and I'll see you next week. Thank you.